So welcome to our talk. We are here to present a way to detect bugs in virtual devices. And our approach is try to compare the virtual device implementation with the physical device. And this is going to be done by me. I'm Kang, and this is Michael. We're from Team DSECT. I bet all of you have all used virtual machines. So I have a few examples here. I put QEMU there, Android emulator, and VirtualBox. Now, all of you use those virtual machines, but I'm not sure whether you pay attention what device you got. So I opened this QEMU VM, then I opened the device manager, and I know it's probably very hard for you to read it, so I can show you that, for example, the display card by default is this Cirrus Logic. Okay? And if you look at the network interface, that's going to be the Intel E1000. This is the default setup, and you can actually have the sync changes. Now, these are virtual devices, which means that you might run a computer that probably using a Broadcom card, but your VM actually saying you are using an Intel card. Okay. And we are actually focusing on this QEMU virtual platform. QEMU is an open source hypervisor, and it also emulates a lot of virtual devices. You might not use QEMU directly, but QEMU share lots of common components with KVM and VirtualBox. And it emulates lots of type of devices, including graphic, network, disk controller, USB. And even within the same type of the devices, you might have different instances of devices. And here I actually list the example of the virtual network interface in QEMU. You see there I have Intel E1000, ePro 100, Novell E2000. You also even have the Realtek 8139. Okay? I want to pause a bit here, ask the audience to say, whether you notice any common characteristics of these pictures and items. So what's common here? It turns out, all these pictures I copied from eBay, okay? And I can tell you, if you trust me, that all this is going to cost less than $10. You probably have thrown away some of this by yourself. Why this matters? What happened is actually all the virtual machines are emulating all these, okay? They're faking this device for you, okay? And these are old crap you already throw away. Now, with all this knowledge, I wonder whether you might have a new way on all these virtual machine and cloud computing advertisement. I always feel all this advertisement funny, like you have people, have the VM is sitting in the cloud, okay? But you might have a different view. But what I want to point out is that virtual machines and cloud really just, they're illusion, okay? You have this, magic carpet flying, life is fine, okay? But you might want to know, at least from the security researcher point of view, you might want to know what is consist of this magic carpet, right? If all the virtual devices are done right, okay, life's easy, everything, people enjoy the, virtual machines, life is fine. But what if the virtual machine are doing something, different? Maybe they're emulating everything faithful, but maybe doing something additional, okay? So something could go wrong. What we are proposing to do is actually to compare the virtual implementation to the physical one to see whether it's really doing a faithful implementation, or does it doing something different? Now, I'm not saying different means definitely something wrong, but that will help you to focus, right? And saying another way to doing this test, and this is a test we call it conformance testing, okay? By comparing the virtual and this physical part. Saying it in the other way, so that's a different way to tell the story. I'm not sure whether this, whether you can tell which movie or movies these characters come from. Or maybe like the audience is too young. These are the Pink Panthers, but one in 1960s, one fairly recent. And you might have seen this. This is the recent Total Recall, and there's the corresponding part. And this is done by our former governor of California. So what I'm trying to say is, what we're doing is really compare the old stuff with the remake, which is really the physical device and the virtual implementation. Okay. Now this actually we already find some interesting results. So I'm gonna get Michael to present what we find. Then I will explain a little bit later to say what's in the detail, how complicated this thing could be. Okay.
So here I'm going to describe some of the possible consequences of what happens if the two devices differ. We were able to discover a buffer overflow in the QEMU E1000 virtual device. And this is caused because this bug happened because of differences in the behavior between the two devices. And the issue arises because the same driver is used for both the virtual and the physical device. And the driver makes some assumptions on the expected behavior of the hardware that it's driving. And in this particular case, the driver expects the hardware to drop packets over a certain size, in this case 1522 bytes, when the long packet enable bit flag is not set. So, in other words, if a jumbo frame arrives, then the NIC should drop this packet. And so, based on this assumption, the driver makes some optimizations on the size of the received buffer descriptors that it allocates. It only just allocates the size that it expects to receive, which is 1522, and it expects anything larger than that to be dropped by the card. So everything in this case works fine on the hardware because the hardware does drop this packet of this oversized packet. However, the QEMU device accepts packets up to a size of 2048 bytes. And what this does is causes the virtual device to overwrite kernel memory in the guest operating system when it does the DMA write of this received packet. So the way we use conformance testing to find this bug is as follows. First, we got one of these E1000 physical devices, and we ran some fuzz testing against it. And while this fuzz testing was running, we recorded the MMIO interactions between the driver and the device and the I/O events that occurred. And then we took the same test and we ran it on a virtual machine using the virtual E1000 device. And the key point here is that even though the fuzz testing was done and there was no immediate crash, we still discovered these inconsistencies between the MMIO register interfaces. And what these allowed us to do is focus on these particular receive events of the fuzz test, which then eventually led us to discover the bug in the end. So now I'm going to let Kang describe how it is that we do this comparison between the two device implementations.
So now, we have this, at least we have this brief information telling you that we can find something. Okay, so how can we find this? By compare two devices. How really can you compare a virtual one versus the physical devices, or even maybe two physical devices? Okay, so first we need to say what defines the behavior of a device. Okay, so in fact, from the software point of view, if you have the device gave you the same register value, react to each of the, if you gave different I/O event, and if two devices gave you the same corresponding register value, we consider, at least from the software point of view, they are the same device. So this is actually very easy to do, to observe from the virtual device point of view, because you have the code, you have all the detail. Okay, you can open up to see, okay, what's the register value, and if this packet arrived, or this I/O event happened, what these register value will be. And it's actually a little bit difficult to do it completely in the hardware, so which I'm going to mention this challenge again later. Okay, but in general, the way we compare two devices is really try to capture its device register values, and also capture the event happened to the device, and we observe the register value before and after the event, then we compare them. Okay, so we have this logging module, monitor all the event, and we dump the device state. Now, since I know some of you might not have the background for hardware, so I'm going to use a very simple example, a very dummy hardware, to explain how we do the comparison. So this is a very simple one. We have a device let's suppose you only have 2 registers. Okay? And there's certain logic built in this device. These 2 registers are related to each other. Register A is actually a mask register of B. Okay? So which means that if you write something to A, the register B is going to update correspondingly. Again, this is a dummy example, but for people who have worked on hardware, you probably know that you have used this type of register set logic a lot. And for example, the interrupt mask, it's exactly the same behavior. Okay? Now, suppose we can observe both of the register, and let's see what we can capture. Now, suppose you read the 2 register value at the beginning, and you also notice that there's an I/O event. This time, in this example, is a memory mapping I/O write and a value to the device. Then, if the device and the logic implement write, you will have the register A updated with the corresponding value from the write. And also register B is going to be updated based on the logic because A is the mask of B. Okay? Now you capture this, recorded both the initial state, the write register action, and the state after. You're going to replay this on the virtual one. You can do this on the virtual device because you have complete control. It's a virtual, so it's just a program. You can stop any time. You can modify any value. Okay? So you take the virtual device, you put in all this value, and then you apply this write request. If you find out that the virtual device has the register value different from the physical one after this event, then you say, okay, inconsistent find. So that's just really a simple idea. However, certainly this is too simple and ideal. In practice, lots of challenges prevent you to do this simple comparison. First, as I mentioned before, not all the physical logic in the hardware can be observed. Okay? So you might have to observe a few interface register, but some of the internal logic, you have to open up the silicon to see it, and which unfortunately is not easy to do, and we don't know how to do it. Right? So you end up only observe a partial state of the physical device, and you can see how that evolved based on the event. There are also other challenges which prevent you to do this comparison easily. For example, some of the events are very expensive or hard to observe. For example, it's probably much easier for you to capture packet than capture the PCI bus. Okay, and additional challenge is that some of the register has a side effect. If you read it, just simply for monitoring purpose, if you read it, it's actually going to trigger a clear, like we call it clear by read register. So when you do that, you're supposed to do passive monitoring of the device state. You might, interfere with the device. Okay. Now, how are we going to solve this? I'm going to present the solution for the first one. We're going to use symbolic execution to allow you to compare the physical device versus the virtual one. Even you can only observe a partial state from the physical device. Okay. Now, before I start explaining with the example, I want to say something about symbolic execution. It is certainly not a new idea. Has become very active nowadays in the security area. And if you're interested, there's a software tool called CLI, and you can go to the website I shown here. And there's a paper, if you're interested more, read the Dawson English paper in OSDI. And there's also a reason some company are doing this, have product, but mostly apply on software. Okay, at least a few there. What we are doing is we're going to use symbolic execution applied on hardware, physical versus virtual comparison. And the approach is that if we have the real value, we will just simply assign those values to the virtual device. If we don't have the real value, we put symbolic value. Now, how does that work? Okay, go back to my simple example. This time, I changed the hardware a little bit. So what happened is you still have 2 registers, but one of them is observable. The other one you cannot read. So from the capture point of view, we know what the register A was the value in it, but we don't know what is register X, okay, which I show in color red. Now, if we want to replicate this situation in a virtual device, all we did is to assign the concrete value obviously directly, but for the one unknown, what we're going to do is we assign a symbol. It's kind of like put a variable there. Okay. Now, how are you going to compare if that's the case? Let's go through example. Again, I assume say you have the access to the virtual device source code, which is the case in the QEMU. But symbolic execution itself actually there are people already extended to work on binary. So even you don't have source code, you might still be able to apply this. But in this example, for simplicity, I'm simply showing you a dumb example. Say in the virtual device, we have the situation if you have the register Rx, which is observable in virtual device, not observable in the physical. If you have this code, and you know that if you have a situation start with this concrete value for Rx, for RA and symbolic value Rx, you're still able to respond to an event. You just cannot deterministically say what is the exact output, but you can say if alpha is equal to 0, you will take this pass, okay? And if alpha is not 0, you take the other pass, okay? Now, how does this affect your ability to compare virtual versus physical device? Well, you can still do some comparison. For example, if just assuming on the left top corner is our trace capture, and you notice the physical device on the observable part has RA equal to, let's say, FFE, okay? And on one of the paths, you don't know which path the virtual device is going to take, but on one of the paths, in this case, we have a match, okay? If you have one match, then you will continue. You will say, okay, likely they're consistent. So we continue. Now also, if you have multiple paths that match, okay, you're going to have to explore all of them. So that's basically the idea of symbolic execution. Okay, so even you don't have all the concrete value, you don't know for sure which path the virtual device is going, you can still explore it. Now, what if suppose in the physical device you have a path, you have a sequence, have the final device state and I/O shows that as a beef, and you can still follow your execution, and you find that by enumerating all the possibility, there's no way your virtual device is going to have that state. Then you can conclude at the moment there's inconsistency. So by using this simple example, I want to show you the power of symbolic execution so that you know that even you don't have the complete state of the physical device, you can still do the comparison between the virtual and the physical devices. So to wrap up, what I'm presenting here is a general approach first to do checking on the virtual device implementation to tell you that you could tell the virtual devices are different from the physical one, and that might lead to some problems. Okay. I also showed you a simple example. Again, I try to make it as simple as possible rather than go through all the detail of the symbolic execution. I hope I gave you a rough idea to tell you that symbolic execution can help you to compare even you only have partial state. Okay? And then our practice also already showed that by using this approach, we can find a lot of inconsistency in the virtual devices, and in fact some of these are known security vulnerability. One of them is from us. We also look at some vulnerability found by others. You should also be able to detect from our approach. Okay, so with that I'm going to conclude the talk, and here's our contact information. I'll be more than happy to answer questions if you have any. Thank you.